Very good. So I'm Adriana Banu. It's very good for me to, I feel it's good to come back. I initiated this program 4 years ago. I ran it for 3 years, and then I realized maybe it's time for people to hear different accent than Romanian. So I'm originally from Romania. I majored in physics, University of Bucharest. Then I moved for PhD in experimental nuclear physics in Germany. I got my PhD from Mainz University. And after that, after my PhD, I decided to come to United States, the land of all opportunities, and try my luck. So first I worked as a postdoctoral research associate at the Texas A&M University Cyclotron Institute. As I said, I'm an experimental nuclear physicist, and there I started my research in nuclear astrophysics, and that will be the subject of today. And after almost 5 years at Texas A&M, it was also time to settle down. So I got a position at Madison University in the Department of Physics 5 years ago. So I'm currently an assistant professor. And what makes my research in nuclear astrophysics more stimulating than in Texas is that now I also get to work with undergrads. And this is a real gem. It's very nice, I'm enjoying. And one of them is actually joining me even today, supporting me. So the topic of my presentation today is understanding the universe, starting from the nuclei to the stars. So I would like to frame our discussion today by the statement of these two great minds. Richard Feynman, once he was asked if in some cataclysm all of scientific knowledge were to be destroyed, and only one sentence passed on the next generation of creatures, what statement would contain the most information in the fewest words? And Feynman answered, everything is made of atoms. Carl Sagan said famously, if you want to make an apple pie from scratch, you must first create the universe. We are star stuff. And with these two statements, we are made of atoms and we are star stuff. We are going to explore our journey from nuclei to stars, trying to answer the two big questions that are at the basis of research in nuclear astrophysics. And those questions are, where do the chemical building blocks of humankind come from? And what makes the stars shine? You are more than welcome to interrupt me if you have questions. Even those who have prepared a quiz, so pay attention, take notes, because we are going to have a quiz using those clickers at the end. But while talking, if you really feel that you need more clarification what I'm saying, do not hesitate to raise your hand. And if I'm on the roll, sometimes I'm too much engaged in what comes next, Gary, you will make sure that that they actually have questions, they raise their hand. So let's start. Let's first start to answer the first question about the element, the origin of the element. What are we made of? We are made of atoms. So do you know what kind of atoms we have in our body? This is the chemical element in your body by weight. So oxygen 65%, carbon 18%, hydrogen 10%, and so on. We also have a little bit of all these copper, zinc, selenium, molybdenum, iodine, manganese, cobalt, iron, all together about 1%. And we also have very trace amounts of these like silicon, lead, vanadium, arsenic. In fact, it's good that we have trace amount of arsenic because this guy is also poisonous. So the question is, where do they come from? So first, let's go back to the atoms. What I'm showing here is a very qualitative description of the atom. What you have inside is the nucleus, which has protons and neutrons. They are also called nucleons. So the protons and neutrons, they are called nucleons. And surrounding the nucleus, we have the electrons orbiting around. This is, of course, not too scary. The atom itself does not have electrical charge. because we have the same numbers of electrons, which are carriers of negative charge, as we have numbers of protons in the nucleus, and the protons are carried of positive charge, while the neutrons are neutral. So the atom is actually most of the time is always quite an empty space. The size of the atom is 10 to minus 10 meters. Also, maybe you are used with this unit called angstrom. 1 angstrom is 10 to minus 10 meters. While the nucleus is even smaller. It's 4 orders of magnitude smaller. So it's 10 to minus 14. So if you have to have kind of an analogy, imagine a football stadium being the atom, and the nucleus is just a marble in the middle of that football stadium. So it's that kind of scaling. So what makes the atoms stable, or maybe unstable? So how do atomic particles interact inside the atoms? And here, of course, I speak about protons, electrons, neutrons, so let's think about it. What do you think? How these particles interact? What are the forces that make them interact? Protons, electrons? Yes.
Never mind.
Oh, come on, you know it. Say it. Say it. 1, 2, 3, go. Yes?
The positives and the
Very
negatives.
good, and okay, let's try like that. So what did we say? The protons are positive, right? And you may have heard that when you have charge-like particles, so positive, positive, or negative, negative, they repel. If you have an interaction between a positive and a negative charge, they attract. So this is what we know. These are electric forces. They have been discovered by Coulomb. So this is why they are called also Coulomb forces. So if you have charge-like particle, like this one here, they will always repel. Doesn't matter whether they are positive or negative. While if they have opposite sign, they attract. So now you think, what makes the atom to be stable? Because inside you have the nucleus, lots of protons there. They are charged like particles, so they should repel, right? So what do you think? What makes the atom? Yes?
The strong force.
The strong force. So just because it's strong will do it? What is a strong force?
It's fundamental force of nature. Is it carried by, is it gluons? I don't know.
Very good, yeah. You know your stuff. So let's look here, guys. Indeed. What makes the nucleus, because here we are discussing mainly about what nucleus has to be stable. So what makes nucleus to be stable, meaning the protons to stick together with the neutrons, is the nuclear force. And it's called strong because it is a short-range interaction, so it really acts between like very, very small distances, and is extremely strong. It's putting this together. And the particles don't really need to be close to each other to feel this force. So the field, the nuclear field, is actually carried on by this glue. In fact, we discussed here about the atoms and the nucleus, but these protons and neutrons themselves are not fundamental particles. They are even more inside each proton and neutron, they are even more fundamental than that, and they are called quarks. So the quarks, they interact, and that interaction is mediated by gluons. Yeah? So indeed, so what makes a nucleus to be stable, I mean the protons to be together, is the nuclear force. What makes the atom to be stable, it is the electromagnetic force. So that governs the interaction between the nucleus and the electrons. And now I have a question for you. The electrons are negatives, and the nucleus is positive. So this means there is an attractive force, right? But if it's an attractive force, the electron can go as close as the nucleus and it can annihilate. Don't you think that that can be possible? You have a negative charge, positive charge. If they attract, they can come as close as possible and then annihilate. So what makes the atom stable?
Neutrons?
No. Neutrons have no charge, have nothing to do. So now we are discussing about this what can make, we know that this is about electric force that makes this interaction, but why they don't come together? Yes.
Because if the electrons were to come closer and closer, then the multiple negative charges would be pushing them apart. So they find a state of equilibrium where the positive attraction from the nucleus and the negative repulsion from the other electrons is equal and they're balanced. They rotate in their orbitals.
No, at the end, I mean, you have your thoughts, they are not completely wrong, but what makes this atom stable, because the interaction is there, so you cannot deny it, is an attractive force, so they should come together. But what we realize, what governs the microscopic world is quantum mechanics. So if this electron is orbiting around, will emit radiation. This is what comes. Every charged particle emits radiation, so it loses energy. So eventually, by losing the energy, the electron will actually come on the nucleus. But quantum mechanics says that the electrons cannot have any energy. If electron were to come down, spiral down the nucleus, will have a continuous energy possible, from whatever it was in the orbit down to zero. But what quantum mechanics says, no, the electron cannot have any energy, a continuous spectrum of energy, only certain. So it's quantum mechanics, it's something that defies intuition, that makes that interaction, makes the electron not to dump on the nucleus. So it's quantum mechanics. So I put here the four fundamental forces in nature: the strong force that explains the stability of the nucleus, the electromagnetic interaction that explains the interaction between the electrons and the nucleus, and we have another two. Weak force is the one who is responsible for radioactivity, and we are going to discuss a lot about radioactivity. And we have the gravitational force, which actually is responsible for interaction between masses. And it's not the subject of our discussion today because this governs the microscopic world. We are now going to focus on the atom, nucleus. So does the nucleus of an atom ever lose particles? So yes and no. If a nucleus is stable, that is because there is a binding energy that is enough to hold all those nuclei together, nucleons together, protons and neutrons. But if the binding energy is not enough, and this means that the strong force can be much less, so it's not as strong as the electric force, is the nucleus is quite big, a nucleus of lead. So in that case, we have a lot of particles there, and the strong force, which has a short range, cannot be enough to keep the stability. So the electric force, the repulsion, can actually win over. So in that case, the nucleus becomes unstable. So a nucleus is stable if the binding energy is good enough to keep it together, and if it is not, it's unstable. So unstable nuclei are called radioactive nuclei because they they tend to lose particles in order to become stable. And when they do that, they change their nature. So you can change an element by emitting radiation. So what is a radioactive decay? It's a spontaneous breakdown of an atomic nucleus, and the result is energy is coming out. Energy or matter. So what kind of forms of radiation are we aware of? Three types: alpha, beta, gamma. What is alpha radiation? This is a nucleus of helium-4. Has 2 protons and 2 neutrons. Beta radiation, it is an electron. And here is something very interesting. This is coming out of the nucleus. So guys, we are discussing now, forget about the atom. When we discuss about radioactivity, we discuss about what comes out of the nucleus. So we said the nucleus will have neutrons and protons. So how is it possible that an electron comes out of the nucleus? Can anyone have a good guess? No. What happened? You have neutrons and protons there, yes?
The neutron splits into a proton, an electron, and another particle that I forget its name.
Bethany, the answer is also here, guys. This is what happens. If you have a nucleus that has, say, more neutrons than protons, there is this possibility that a neutron is transformed into a proton. In physics, we conserve charge and we conserve mass number. And we will discuss in a minute what means mass number. So here you have a neutron which has a charge 0. If an electron, if it is transformed into a proton has a positive charge. So an electron has to accompany that in order to annihilate the charge of the proton. So plus 1 minus 1 makes it 0. So an electron comes out of the nucleus is because the neutron is converted into a proton. And it can also happen the other way around. If you have a nucleus that has more protons than neutrons, in that case the proton is converted into a neutron. And in that case, the particle that is emitted is a positron, is the antiparticle of the electron. Is a particle that has exactly the same mass like the electron, but positive charge. Yes?
I was going to ask where the mass came from for the electron.
No, this is, as I explain in a minute, it is energy is released. So so in order to, so you start with the mass of the neutrons, you go into the mass of the proton, and energy is released in that decay. So that takes care of the electron. So it's energy. You have to balance the energy there. Yeah. And then another form of radiation is also gamma radiation. These are photons, like light. If that happens, means that nucleus gets excited, gets in a higher energy than normally is, which is called ground state, the equilibrium energy. So if it gets a form of excitation, energy from outside, gets excited, and doesn't like to stay there, and will emit photons. So when a photon emission happens, the nucleus remains the same. It just goes from a high energy to the lowest possible. So now I want to discuss a little bit how much energy actually comes out of a radioactive decay. So let's take an example of radium, 226 nucleons, meaning has 88 protons and 138 neutrons. If an alpha particle is emitted, meaning we lose 2 protons and 2 neutrons. Therefore, the daughter, we call this parent and this is daughter, the product of this decay is going to be radon 222. 86 protons, we are losing 2 protons, and we are losing 2 neutrons. So now, if we start 1 kilogram of radium, 226, and then we convert that by alpha decay into radon, this much mass is lost. So the mass difference is going to be tiny, 23 milligrams. However, if you use Einstein equation E equals mc squared, delta mc squared will give us how much energy is actually released in the radioactive decay. And that is huge, guys. I put it here in joules, but just to give an equivalent, it's 1 kilogram of radium by alpha decay would be equivalent with 400,000 kilograms of TNT. So it's that powerful, a simple alpha decay. That much energy is released in alpha decay. So it is so powerful that the robots that are sent on Mars, the rovers, they are actually powered by a plutonium-238. Because in that emission, alpha emission, a lot of energy is enough to power the robot. Now, I discussed about energy emitted in a decay, in a radioactive decay. The same thing happens in a nuclear reaction, something that you want to create a nucleus. So for example, I'm giving you here, let's make a helium-4 nucleus, an alpha particle. You start with 2 protons, 2 neutrons, and you want to make that nucleus. And if I were to ask you which one is, if I put them on a scale, so which one is heavier, is actually these protons and neutrons, when they are by themselves, they weigh more than this. So this means that if I were to make such a nuclear reaction, I would actually lose mass, because there is a mass loss here. I'm going from something more to less. So again, that loss of mass is equivalent to a lot of energy being released, delta mc squared. So what we discussed about binding energy is this energy that is actually released in a nuclear reaction. Now, if you discuss with any chemist, they will show you the periodic table of elements. I started with that. By a nuclear physicist, we are working what is called chart of nuclei. So what I'm giving here is a representation of neutrons and protons in a nucleus. So if I have to group these nuclei, which we also call them nucleids, by the number of neutrons and protons inside. This is what would be the laydown. So let's give you a description. The black holes are the ones that are stable. They do not emit radiation. And how many there are in nature? About 300. 3,000 are the ones that are colorful, and those are radioactive. So meaning that they have to decay. The ones in red, they decay by emitting an electron. And why? Because they are more neutron rich. They have more neutrons than protons. And the other one that are in blue, they are decay by emitting a positron because they are more proton rich. So a proton is converting to a neutron. So about 10% of the isotopes that we know in nature, nuclei, are unstable, and only 10% are stable. And theoretically, we predict 7,000 to actually exist. But we only know currently 3,000 of them. Some of them in yellow decay by alpha particles. These are the ones that are very heavy. And in order to become more stable, they have to release a heavier particle in an electron. And some of them spontaneously fission, break them apart. So a chemical element, when we discuss about an element, has this kind of symbol. So this is the chemical symbol, this is Z, the atomic number, meaning how many protons I have inside, this is how many neutrons I have. And A here, it is the mass number, so it is the sum of the protons and neutrons. And because the protons and neutrons have much more mass than the electron, basically the mass of the nucleus is carried, of the atom is carried by the nucleus. This is why it's also called mass number, A. Now, let's come back to our big question. What is the origin of this element? We see them on Earth, we see them in stars. So, where they are coming from? So originally there were like two theories. What I'm showing here on the left side, Big Bang. This idea was promoted by George Gamow, a Ukrainian physicist. He said that all the elements are made in Big Bang. How? By neutron capture followed by beta decay. And on the other side, we have another model that says no, heavy elements have been made in stars or stellar envelopments by nuclear reactions. So which one is right? We have a Nobel Prize in each category. So which one can be correct? To answer that question, we have to investigate the property of nuclei. And coming back to, I think here is a good story, I should give it away. So George Gamow was the one who initiated this idea, and he worked with his assistant who had a last name Alpha. So this gentleman in the middle here, his name is Hans Bethe. He's a theorist, the first theorist who explained the nuclear reactions that happens in our sun. He was the first one, before doing any experiment to prove that. He was the one who laid down. And he got Nobel Prize because of that. The reason he's in this category with the Big Bang is because the scientists, unlike the politicians, we like to disagree and we are respectful about each other, and we even push it further. George Gamow said, what fun it will be if we have a paper which will be entitled Alpha, Beta, Gamma, following their last name, Alpha, Beta, Gamma. So he just asked Bethe, do you want to be on my paper? Bethe did not believe in Big Bang nucleosynthesis, but he said, why not? So he did not fear that his reputation would be damaged. So he accepted to be on this paper, which, as we'll see in a minute, it became an infamous paper because this theory proved to be wrong. So why is it wrong? Now, what happened in the Big Bang? We discussed a little bit in the introduction about quarks and gluons. So these protons and neutrons are made of quarks. Within the first 3 minutes, from the Big Bang, the state of matter was what is called quark-gluon plasma. So it was a mixture of quarks, and their interaction was mediated by gluons. This is how the protons and neutrons have been formed. But then, once the universe expanded, cooled down, the temperature also went down, whatever was possible to be synthesized, this is what we call nucleosynthesis, to actually make the elements by nuclear reaction, whatever could be synthesized in Big Bang was only hydrogen and helium, a little bit of heavy hydrogen, we call this hydrogen 2 because it has a proton and a neutron in addition, and a little bit of lithium and beryllium, but no other heavy elements. And why is that? Why is it not possible to create other elements? What I'm showing here is a small segment of the chart of nucleus. We have the neutrons and the protons. Oops. Sorry. So what I'm showing here are the stable nuclei. So we start with the proton, here hydrogen 1. We have here and hydrogen 2, the heavy hydrogen. So now, Gamow said that everything is made in Big Bang by neutron capture, followed by beta decay. So let's follow here. I have a proton, and if I capture a neutron, I make heavy hydrogen, hydrogen 2. Fine, this is stable. What happens if I capture another neutron? If I capture another neutron, I move here, I get more neutrons, yeah, and I make it hydrogens free. This is also called tritium. This is radioactive, does not exist, it cannot stay there, it's not stable. So then what will happen? Because it has more neutrons, will decay by emitting an electron. And as we explained, in an electron decay, beta decay, a neutron becomes a proton. So basically you are losing a neutron and you are gaining a proton. So what you are making? Helium free. So from here, you go up in diagonal, you make helium free. If you capture another neutron, you make helium-4 alpha particle. But if you capture one more neutron here, you make helium-5. And helium-5 does not exist in nature. Therefore, cannot decay here by beta decay to make lithium-5, and there to make lithium-6. So you have a gap here. This mechanism of neutron followed by beta decay cannot happen. However, Gamow said, yeah, but somehow lithium is made in Big Bang. So, okay, I don't understand this, but if I make lithium, I can make the other. No, the problem is that if you make lithium-7, if you capture another neutron, you end up with lithium-8. And again, in nature, there does not exist element, is not stable with mass number 8. So if you don't have this element, you cannot go here, and you cannot create beryllium-9 and also on. So you cannot build anything heavier than that. So because in nature there are not these mass stable there are not nuclei with mass 8 and 5 existing, this theory of creating everything by neutron capture and beta decay is wrong. So then the other model that can be valid is everything happens in stars. Everything heavier than hydrogen and helium. So how the stars are formed? We had the hydrogen and helium from the Big Bang. Then this gas is all over, and then gravity puts it together. This is how you make a star. But if the gravity is acting on the star, it's compressing the matter, so something has to hold that pressure. So it so happens that that thermal pressure is created by a nuclear reaction. As we explained previously, if you make a nuclear reaction, always energy is released. Because the idea of a nuclear fusion reaction is to create more stable elements than the participants. So in that nuclear reaction, energy is released, and therefore that energy can balance the gravity. If that balance doesn't happen, the star can explode or can go in a black hole. So all the elements have been synthesized in stars by nuclear reaction. So the nuclear reaction can explain the energy production, why the stars shine, and also how the elements are synthesized. So once the star explodes, and when that will happen? When there is nothing that can balance that gravity. And I will explain more when that can happen. So this star explodes, all the elements that have been created will be expelled in intergalactic medium, and then again gravity will put them together and new stars will form, which will be more enriching elements than the previous stars. And this cycle, guys, even happens as I speak. So this nucleosynthesis, formation of elements by nuclear reactions in stars, is an ongoing process. Now, something that we have to understand, if we have a nuclear reaction, so I put here two nuclei interacting, always we have to conserve, to determine what will be the products, we have to keep in mind that the mass number has to be conserved. So what we have initially has to be equal to what we have finally, and also the charge. So the sum of the charges of the nuclei initially has to be the same after the reaction happens. And this energy will be released. As I explained, the nuclear fusion happens when the particles that are formed are more stable than the original ones. So therefore, more stability means less mass. So therefore, we are having a deficit of mass, and that is the equivalent delta mc squared with energy loss. So in a nuclear fusion reaction, always energy is formed. If the products have a higher mass than the original nuclei, that reaction cannot actually happen because you need to put energy to make it possible. So you are familiar with the nuclear fission, which means, because this is the only way we can get on Earth energy out of nuclear process. We are splitting and having nucleus in two lighter ones, and in that process, again, because we are losing mass, we are releasing energy. This we can do without any problem. However, we cannot do on Earth the reverse reaction, fusion, which in stars happen naturally. Because here we are dealing with the reaction between light charged particle, which means the repulsion is very strong. In stars, we have the right temperature and density condition to make that possible. On Earth, it's extremely difficult. So this is why we cannot have fusion make possible on Earth to create nuclear energy, which will be a much cleaner way than the fission. But there are ideas, so we are still working on that. So hope is there that eventually we can also realize this process on Earth. Now, what I'm showing here, which is very important for understanding of the synthesis of heavy nuclei, it is the mass number, that A, the number of the sum of the protons and neutrons in each nucleus. So if you ask yourself, what would be in average the energy that is needed to bind a nucleus, a nucleon, doesn't matter whether it is proton or neutron, inside the nucleus. So what I'm showing here is the average binding energy per nucleon. So how much energy I need to bind the proton and a neutron inside the nucleus. So the distribution here is that we can go up to iron, and then in average we have about 8 mega electron volts. Mega electron volt, it is 1 million electron volts. Electron volts is a unit for energy that we use in nuclear reaction. So in nuclear physics. So by fusion, we can create all the elements up to iron, and we cannot go beyond because, as you can see on this graph, iron is the most stable nucleus. So you cannot fuse any more iron and iron to make other elements, because in that case you cannot make anything more stable, so you don't release any more energy. So in stars, we can only make nuclear fusion up to iron. Beyond iron, you cannot anymore have reactions that lose energy. Beyond iron, the only way you can get energy out is by fission of heavy elements into lower. But fusion beyond iron is not possible. So if you have in mind that, let's look what happened in a star like our sun. Our sun is not a big star in terms of the mass, doesn't have enough mass to synthesize elements up to iron. The only element that can be synthesized in our sun is alpha particle. So we start with hydrogen from the Big Bang, and we make a nuclear reaction between 4 hydrogen nuclei, make a helium. So we do not have enough temperature, because the way you get temperature in a star is by mass contraction. Our sun doesn't have enough mass to create, by contraction, enough temperature to trigger the nuclear reaction beyond fusion of helium. So all we can do is convert hydrogen into helium. And the reaction to convert hydrogen into helium is pretty slow. For example, to make 2 protons together to form a heavy hydrogen, that reaction happens once in a billion years. Because this reaction is extremely slow, this is the reason our sun is still in the half of his life cycle. So, because if you run out of fuel, if all the hydrogen is immediately converted into helium, you cannot anymore release energy, and you cannot anymore support gravity. So therefore, our sun eventually will explode. But because this reaction is extremely small, 1 in a billion years, this is the slowest one in this chain, our sun can still have another high, so it is 5 billion years old. We need another 5 billion years old until all this nuclear fuel will be exhausted. Okay, how can we make carbon? Carbon-12 is extremely important because carbon for our life, because carbon-12 is made of 3 alpha reactions. And take a look here, why is this magnificent? If you have an alpha particle interacting with an alpha particle, what you create is beryllium-8. And as I explained when I discussed about Big Bang, beryllium-8 is not stable, does not exist in nature more than 10 to minus 16 seconds. And after that is transformed. So how can you make carbon-12? You need another alpha particle. Because as I say, you need to conserve mass and you have to conserve charge. Alpha particle has 2 protons and 2 neutrons. Carbon-12 has 6 protons and 6 neutrons. So you need 3 alpha particles to make carbon-12. So look, our life, our existence depends on these statistics. In this tiny time, 10 to minus 16, which is the lifetime of beryllium-8, if another alpha particle comes, you can make carbon-12. And we are carbon made. So if that reaction will happen, we will never exist. Because this is the only way you can actually start creating heavier elements beyond helium-4. Now, the problem is that once carbon-12 is formed, if another alpha particle interacts with it, it can make oxygen, 16. Oxygen is good for us. We depend on oxygen too. But if this reaction happens much faster than carbon formation, you can destroy, you can consume the whole carbon. So if you consume carbon, again, we cannot exist. So it so happens in nature, all these are very well matched, that this reaction rate, meaning how fast can happen, is quite small. Therefore, not all the carbon was burned. We call it burn when it is exhausted. So hence, carbon-based life like us was possible. Now, if a star has a much bigger mass than our sun, it can convert elements up to iron. So it starts with a core of hydrogen, it's converted into a helium, then a helium can be converted, as I explained, into a carbon. Carbon can fuse with another carbon and make a neon. Neon can actually be disintegrated by photon and can make oxygen. Oxygen and oxygen can make silicon, and silicon, 2 silicon can fuse, make iron. But once you form iron, you cannot expect to synthesize, and these two will ever fuse because iron is the most stable. So to make other stable nuclei more than iron is not possible. So in that case, if a big star like this ends up with a core made of iron, cannot support gravitational contraction. So therefore that star will explode. Can either explode like a supernova, or can also become a black hole. Which of the ways possible, that is again is a probabilistic process, so we don't know. So our understanding is that the elements heavier than iron have been formed in supernova by neutron capture. So now the idea of Gamow, of capturing neutrons to make heavy elements, actually works here. So this is an example of supernova in 1987. And now let's go back to the formation of our solar system. And as I said earlier, our solar system started about 5 billion years ago with a contraction of hydrogen and helium, whatever was in the universe. And the elements that have been found in our solar system are this one. So what I'm showing here is the abundance of the elements in our solar system. So this is their mass number, and this is the abundance. The most abundant, of course, is hydrogen and then helium. And they're formed by Big Bang. And all the others, up to iron, are formed by nuclear fusion reactions in stars. And beyond that, beyond iron, this is $1 billion question. We think that they are formed in supernova, but we have to prove that, what process is possible, and in which environments. So the abundance of elements and all the isotopes are unique fingerprints of these various cosmic processes. And to understand and interpret what does it mean all these peaks here, you have to understand nuclear physics. All these are property of nuclei. So this is an unsolved problem. And in fact, more than 10 years ago, 11 questions for the new century have been posed here, and how the heavy elements have been formed from iron to uranium made the list. So this is still valid, even 13 years, 12 years later, we still have this list, and this is a valid question. Now, to summarize, what I'm showing here is this landscape of a chart of nuclei. We have the neutrons and the protons. Everything in black are stable nuclei. Everything in green, these are radioactive nuclei, which we know about their existence. They occur on Earth. And everything else in yellow, these are expected nuclei, all radioactive. And we think that elements up to iron, we are very sure about it, they are made in stars by nuclear fusion, and everything beyond iron, we think that half of them are made in supernova by neutron capture, fast neutron capture. When I say fast, it's fast with respect to beta decay, because once you have a neutron-rich nucleus, can either capture a neutron or can decay by emitting an electron. So if the capture of the neutron is much faster than the decay by electron, you can create all these elements far away from this valley or stability. So this process here is called R process, meaning rapid neutron capture. This is a theoretical description of the past of this rapid neutron capture process. Now, as experimentalists, we have to make these nuclei on laboratory, and we have to study their properties. We have to study their nuclear reactions and make sure that actually they match what the theory says. If the neutron capture is much slower than the beta decay, then we have what is called slow neutron capture, or the S process. So these are nuclei that are actually formed around the value of stability. So they capture a neutron, but then they immediately decay, and then into a stable nucleus they capture a neutron. So they kind of are zigzagging along the value of stability. So half of the elements beyond iron are made in star and supernova by the R process, and the other half by S process. The question is now what happened with the proton-rich nuclei on the other side of the value of stability. This I call the P process. These nuclei are still under investigation, and this is my contribution. So my research is about understanding how these proton-rich nuclei, heavier than iron, have been formed. And they are particularly interesting because they are also very rare. So if I'm showing you here the abundance of the elements, these P nuclei, as you can see here, have much less abundance and is in logarithmic scale than the other ones. So it's extremely difficult to measure them because they are so rare. And the way you can study their reaction is actually by not using charged particle reactions, but using photons. So when a photon carrying energy interacts with matter, can disintegrate that nucleus. And in that process, a neutron can be emitted. So if you are losing neutrons, you are actually creating more proton-rich nuclei. So my research, and they are also called in nuclear astrophysics peanuts, because they are so little in abundance with respect to the other. So basically, I'm studying peanuts. So I will give you a little bit of highlight of my research about these P nuclei. But what I'm telling to my students, first of all, before you start to understand how the nuclear reaction fuels our stars, you have to understand the tools of the trade. So what my students learn in my laboratory is they have to study how the ionizing radiation interacts with matter, how charged particle photons interact with matter. They have to understand how you can detect that radiation, so how that detection works. Also, we need to set up the experiment. We have to actually set up the electronics. We have to set up data acquisition, and then you have to do programming. A lot of programming. You have to, how do you interpret these results? You have to do data analysis. So for that, a lot of programming, you have to code a lot. And after coding, you also have to do a lot of simulation, because most of these reactions we don't know about them. So we have first to simulate what is the outcome, and then do the experiment and check how that matches with our simulation. And then ultimately, if we do a good research, we have to publish our results and disseminate them in conferences. And as early as last spring, we had an experiment. This is my student Evan Mickens, who is going to entertain you in a few minutes with a quiz. So we did an experiment at Duke University using the Higgs facility. Higgs is not the Higgs boson. It is the high intensity gamma ray source. It's the most intense gamma ray source in the world. So basically we accelerate electrons and then we produce photons, and by this interaction between photons and electrons, we can produce relativistic photons, something like 20 MeV, enough to actually simulate the reaction that happens in stars. So we did that experiment. Now data analysis is in progress. And as early as October, after the experiment was done, Eva went to Hawaii. So it's also to entertain you doing research. It's also you have the benefit to go in these nice places like Hawaii to present your research. And if you have time after my presentation, you can chat with Evan what it means for an undergrad to have this kind of first row experience at one of the to say state-of-the-art facilities in the world, and this is at Duke University. Now, message to take away: nuclear reactions play a crucial role in the universe. They provide the energy in stars, including that of the sun. They produce all the elements we depend on, and the nucleosynthesis again is an ongoing process. So there are about 300 stable of these nuclei in the universe. And by studying the nuclear reaction, we can produce 30,000 more of them. These are radioactive. But then there are still 4,000 up to scrutiny. We know that they should exist, but we have not produced them yet. So to produce them involves the next generation of accelerators, because you have to accelerate these charged particles. It's extremely complicated, but not impossible. So maybe it is up to some of you to take part in that quest. And actually the message you should take away is it's true, what your parents have been told you. You are indeed star material. So with that, I would like to conclude my presentation, and if you still have questions, we can maybe allow 2 or 3 questions before we go into the quiz session. So are there any questions? Yes?
I know earlier when you were saying something about the 5 and 8 nucleides that aren't able to don't exist.
So
What's the difference between something just being unstable enough that it instantly decays and something not even being able to exist?
So it's the time, right? Once you make that beryllium 8, it only exists for 10 to minus 16 seconds, and it's gone. If it is radioactive nuclei, it takes a time, so it has maybe a minute, 2 minutes, so the half-life can be even, like uranium, for example, is a radioactive nucleus, but the half-life of that uranium is bigger than the life of our solar system. So it is how long they stay in that state that make them, radioactive versus unstable. If they just immediately disintegrate, like 10 to minus 16, they don't exist. You don't see them. But if they stay around, minutes, days, years, they are radioactive, but it takes a time. Because this is a probabilistic process. It's again involves quantum mechanics. It doesn't happen spontaneously.
Yeah.
Other questions? Guys, we are going to have a quiz now, and we want to make sure that because we also want to give you a college experience. Okay, so you have very passionately took notes, and maybe you also try to understand what I'm saying. Now we're going to have a quiz and see how much you have understood. So how this is going to work? You have to. Everyone has the clicker. The clicker has to have channel 51. So if you click on the menu, for example, that orange button, you should look in the upper corner and see in upper left corner what number is there for channel. Do you have 51?
Yeah.
Everyone has 51?
No. I got nothing.
You have to click on the menu. It's the orange button.
Yeah, there's nothing. There's nothing coming up at all.
Maybe there is no battery.
Perhaps.
So try mine.
Let's see. Yeah. Oh.
Yes, you click the.
You have said leave presentation mode.
And you say no because you. So if your channel is 51, you don't leave the presentation mode. If your channel, raise your hand. People who don't have channel 51. Okay, what you have to do is asking you leave presentation mode. You say yes. There is a button there, yes, yes. You click yes, and then it's asking you change channel. Scroll down with yes because there is that arrow for down, and then change channel. And once you click there. Everyone click on change channel? Yes? Then you change, it's asking you put 51 and then say enter. You did? You have? Everyone has 51? Okay, let's give it a try. So now Evan Meekins is is my research student. He's a junior in our physics department. He's also majoring in math. And he has been working with me since he was a freshman, and not only that, he's supporting me all the way. So he's going now to entertain you with this a short quiz. We have something like 8 questions prepared. So maybe let's make sure that they don't. Let's have this quiz first coming up. Okay, so maybe Evan is going to read a question for you. Since I switched it off.
Okay. So, yeah, I'm Evan. Do you guys have any questions about research opportunities for undergraduates, being able to go abroad, to go to conferences and whatnot, or what JMU Life's all about? Anything I can answer? Anything.
Oh, I hope I did not exhaust your mind. I challenged you that much? No. We will see how you answer this quiz as soon as the projector is up. Maybe we can just have the poll. They are already. We can still ask the question and then they will answer it and until this comes. No, don't say oh, because if you say oh, people say oh. Okay, so let's ask the first question.
Okay. So we're having some technical difficulties right now. I apologize. But I'll just ask you the questions and tell me which thing poll in. So I'm going to give you 5 statements and one of them is going to be false. I need you to tell me which one is. It's not like I know. So 1, the nucleus has an overall positive charge. 2, the nucleus takes up a very, 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 very small amount of space. 3, the nucleus contains both protons and neutrons. 4, the nucleus repels the electrons around it. And 5, the nucleus contains most of the mass of the atom.
We'll give you 30 seconds. So you just click the number you think is correct. I mean, in this case, it's a trick question. You have to look for a false answer. The projector, I think it takes some time. They're very old.
You have to press enter after you.
No, just press the number.
Just press the number. You can also change your mind during this process because you still have 3 seconds.
2.
1 time down.
Okay.
And then I see. Okay. Unfortunately, we cannot show you the results, but.
So most of you are right. Some people said the nucleus has an overall positive charge is wrong. The nucleus is made up of protons and neutrons. The neutrons having a neutral 0 charge and the protons having a positive charge. So the right answer was that the nucleus does not repel the electrons surrounding it. So.
Something's wrong with that one.
Okay, and I think this guy is going to come soon.
Okay.
I can see.
So I'll come back to life.
the two statements, the one that said that the nucleus takes up a very, very small amount of space, and the one that says it takes up most of the amount of space. How could
Sorry, it takes up most of the mass.
Okay, sorry, Matt. Sorry.
It's of a extremely dense, small
Okay, now,
object.
sorry, I was-
Okay, good.
Okay. Okay, so there, that was the right wrong answer. So
Next.
okay, so here's the next question: which of the following processes cannot transform one element into another? So I'll give you 30 seconds. The first one is alpha decay. The second one is gamma decay. Third one is nuclear reactions. The fourth one is beta decay. And the fifth one is none of the above. Okay.
Ooh.
Okay, so to those who answered none of the above, why do you think that is? Does anyone want to think about why that is? Why none of these would, or why none of these would be able to keep an element or an isotope the same?
Guys, you want to have lunch? So let's be done with this. So, none of the above. Why is that? Hi, step up. Yes.
Well, didn't you say earlier that two alpha decay particles colliding can form one nucleus? Is that considered two elements forming a different element?
So when we're discussing about the radioactive decay, means one particle is released, can be an alpha particle or an electron, and something else is formed, right?
Yeah, what you're talking about is technically called fusion. So, and that would be lumped under nuclear reactions.
Well, yeah, that's my point. My point is, couldn't it not be none of the above?
The right answer is gamma decay, because gamma
Right,
decay
because
is.
it doesn't form any particles. It's
If you have a nuclear reaction, you will form something else than what you had initially started with, correct?
Right.
So a nuclear reaction will transform an element in something else.
I think what
So,
he's
so
saying.
the question is, which of them cannot make that transformation possible?
Yeah, what he's saying is 5 can't be right because he knows one of them at least has to be doing
I
what it
understand.
says.
Okay,
So.
very good. Okay,
Yeah.
I see.
Yeah, all gamma decay is just a new.
Photons, super high wavelength.
Yeah, there's no mass, there's no charge, nothing, not even a neutrino. So it's just pure energy being released. So, okay.
But by none of the above, we meant all of are wrong.
Okay, so next question. We have two atoms, one of them having 6 protons, 6 neutrons, and 6 electrons. The other one having 6 protons, 8 neutrons, and 6 electrons. And which of the following best describes the difference between them? So,
30 seconds.
same number of protons and neutrons, but different number of, or same number of protons and electrons, but different number of neutrons. Okay. Okay, so it must be, you got that right, so that's good. They're just two different isotopes, meaning that they have different number of neutrons. Certain isotopes can be stable, some of them can be unstable. So it just depends on which isotope you're talking about. Okay? And the next question is, what is nuclear fusion? Which of these best describes nuclear fusion? Is it splitting of heavy nuclei, the combining of electrons, fusing two light nuclei, releasing gravitational energy, or releasing chemical energy. Okay? Nice. Almost all of you got that right. So, yeah, nuclear fusion is just taking two relatively small particles, colliding them together, and then you form a new particle. And if it's stable, then it stays together. But a lot of the time, as with the two heliums coming together, they'll form an unstable atom, which will just break apart. Okay?
Let's see whether it's possible to get at least one question correct 100%, everyone here. Let's see, maybe this one.
Okay. The most stable element in the universe is you have hydrogen, carbon, uranium, helium, and iron. Okay?
Oh my God, you blew this off.
Almost. Almost. At least no one picked uranium, so that's good. That's good. But yeah, hydrogen was the first element, so you need that in order to get further on, so it can't be perfectly stable. If two hydrogens come together, then they'll form a helium or two hydrogen. So it's really iron because in a sun, the core is iron, and that's the hottest point. So if nothing can go beyond there, then that has to be the most stable. So, okay? Let's see. Oh, we have another one. If you wanted to find an atom in your little finger that has been in its present form since the beginning of the universe, which element should you look for? So if you want to look for something that's been there since the beginning of the universe.
This one you should get it absolutely right. All of you. Unless you want to make fun of them. That is also possible.
My little finger hasn't been around since the beginning of the universe, so it doesn't make sense.
That's a trick question.
Don't press number 7. 7 does not exist.
The oldest element is? Okay.
Oh my God.
We almost got it, so. Okay, yeah.
Catherine, are we 23 people? Because could be sometimes these clickers, they have some fake numbers. So are we 23? Huh. Sneaky monkey, some of
So, yeah, hydrogen was really the first element created, and all the hydrogen that is in the universe came from the Big Bang. So you can't create hydrogen. You can split off different hydrogens, but hydrogen's always been there. So.
And you remember that abundance curve with hydrogen being on top of it, the highest peak, and everything else going down. Okay? Next one.
Okay. The fact that our bodies contain heavy elements like iron means that, so what does it mean that we have very heavy things in our body? We have iron and bismuth.
And yet we are in this solar system. And our sun cannot make elements heavier than helium-4.
Okay? Oh, this is split. This
Whoa.
is fun. Okay. So half of you are saying that there were earlier supernova explosions in our galaxy, and the other half of you are saying that these elements were synthesized during the Big Bang. And
How is possible? So you are with Gamow? George Gamow was wrong, guys. George Gamow was wrong. Elements are not made, all of them, in the Big Bang.
you could argue that there were really 4 elements made in the Big Bang. You know, hydrogen, helium, lithium, and boron. But besides that, Oh no, sorry, beryllium. But besides that, everything that we know that's heavier than iron has been made from extremely energetic supernova explosions. Without those, we wouldn't have any uranium. We wouldn't have any plutonium, any lead, none of that stuff.
But to add on that, so okay, so what happened? This supernova exploded, the heavy elements were there, and then what happened? When the new star has been formed, like our sun, that element, that intergalactic medium was not pristine, had this contamination of heavy elements, and then gravity put all together these heavy elements, but then our sun has that much mass. So even though there are heavy elements in our sun, they are not synthesized in the sun per se. Our sun can only create helium out of 4 hydrogen. But the other elements are present because this has happened when the gravity put together the gas to make our sun. You understand? Heavy elements were produced in other bigger stars that exploded. All these elements were expelled, and then gravity put them together, make our little ball sun with that mass, and only helium. So make no mistake, our sun will never go supernova. It will become actually a white dwarf, little star, but will never go supernova. We cannot synthesize elements beyond iron in our sun. And we don't care because we are not going to be around. 5 billion years from now is going to happen. So I think this is all we'll have for you. So let's, I thank you for being patient. You did well, guys. You can graduate. And then let's also thank Eva for helping us here.
And then if anyone has any questions about JMU life or physics or opportunities, both undergraduate and graduate, please don't hesitate to talk to me.
Oh, look, I was wrong. There is one more. Guys, can you stay for one more before lunch? Yeah. Let's get this 100% correct and take a photo with this.
Okay.
Oh,
100%. That is 100%.
we are too fast. We get away the answer.
That is 100%.
It is.
But I wanted to make them to be made by them. This happened in college too. Sometimes we give away answers. But anyway, you did well. I'm proud of you. So hope you enjoy, and let's start next week on our quest for understanding atomic physics. So next week will be atomic physics.